To get confirmation, go ahead and begin. Okay, so it looks like it's recording. So we're going to start today by talking about cooling and dehumidification. We're going to work the example problem that's been posted on Canvas on cooling and dehumidification. And then on Monday, we'll come back to the adiabatic mixing case and work an example problem with the adiabatic mixing. So that is the plan for today. Otherwise, before I forget about it, I want to let everyone know by the end of today, we'll have covered, I think, almost everything that you should need to know for the reading quiz. So you should be able to complete the reading quiz over the weekend on psychometrics. So there's that. And then also just don't forget that there is the homework for the basically the psychometric processes that we're talking about. After today, when we work our first example problem, you should be able to do most of that homework set, or at least be able to attempt most of that homework set. So those were just the general notes that I wanted to kind of start with. Otherwise, let's go ahead and get into the details about cooling and dehumidification. So in terms of cooling and dehumidification, the standard way we're going to approach this is kind of as one process. And so the way that we're going to, for the most part, I should say, be able to remove water vapor from the air is we just cool the air down past the saturation point and we let water condense out of the air. And so in our analysis over here, what we're going to have is we'll have some dry air coming in and going out. We'll have some water vapor coming in and going out, and we're going to have then some water that also leaves the system. And so we're going to have three flows of water that we're going to need to consider. We'll have some mass flow rate of vapor coming in, we'll have some mass flow rate of vapor coming out, and we'll have some mass flow rate of liquid water that is going to come out of solution. Now what we'll eventually be able to show is that we'll get the mass flow rate of this liquid water be the mass flow rate of the dry air times the humidity ratio difference. And so we'll show that here on the next slide, but we'll be able to do some psychometric relations here to take a look at how much water we would have condensed in our process. And so if we go back a few slides, we had talked about how the basically the process would work on the psychometric chart. So if we start with a state point right here, we'll call this state point 1. To do the cooling and dehumidification process, well, we'll start by doing simple cooling. And so simple cooling was just a motion to the left on the psychometric chart. And we will cool it all the way until it reaches the saturation condition. The saturation condition is basically going to be like right here on the system diagram. So right before we start to have this water condense. And so this process, again, is simple cooling. This portion will have a constant humidity ratio, and that will go all the way up till we get to a relative humidity of 100%. Once we hit the 100% humidity or relative humidity, we will continue cooling it. But since we can't go past 100%, what we're going to do is we'll move along this line of constant saturation, and so we'll move down here, and I'll just go ahead and say cool it down to about 10 degrees. We went a little past there, but we'll say right there. And so this will be our final temperature. Now, whenever we do a cooling and condensation case, the exit state is always going to be at 100% relative humidity, because we have to have it at that saturation point, because we've up until this point we've just been cooling it, and as we continue to cool it, we continued to have more and more water come out of solution because that was the saturation condition. And so in this case, cooling is going to be the way that we get the water to come out, because we hit that saturation point. And so that is the key thing to note. We could say also, in this case, relative humidity 2 will always be greater than the relative humidity 1, because the relative humidity at 2 always has to equal 100% if there was condensation. So again, if condensation occurs, relative humidity is going to be 100% at the end of that process. Now, in some HVAC applications, we're going to say, well, we want this to be done for human comfort. human comfort isn't going to necessarily be achieved by having this at a 100% value. And so this is just the cooling and dehumidification case. I'm adding this as kind of an extra comment. So this is just kind of something to think about. In terms of comfort, we want things to be about 30 to 60% relative humidity. So if we were going to do dehumidification for, say, a large building, so it's summertime, we brought in hot, moist air, we need to cool it down, we need to have the humidity be much lower. What we'd do is we'd first do this dehumidification process, but then to get it back into human comfort areas, we would go ahead and add a little bit of heat until we reached a comfort level temperature, comfort level in terms of our relative humidity. So sometimes we will heat that back up, but in terms of the cooling and dehumidification case, whenever we leave that part of the system, it will always be at the saturated condition. And so again, this extra part was just done as far as like an HVAC actual application for human comfort, but I'm going to go ahead and just erase that because I don't want you guys to confuse that with the cooling and dehumidification process itself. Okay, so let's go ahead and take a look at the mathematics on this, and then we'll go ahead and work the example problem that we have. So in terms of the mathematics, what we have is air coming in. So air will have a mass flow rate of dry air coming in, and we'll have a mass flow rate of dry air leaving. We'll have a mass flow rate of vapor leaving. We'll have a mass flow rate of vapor entering. And then for the condensate here, we'll have a mass flow rate of liquid water leaving the system. And so what we need to start with is a mass balance. And so if we go ahead and apply conservation of mass, and we focus on the air side of the system, the air side will have the change in mass of air with respect to time inside the system. Steady state will have the mass of the air at state 1 minus the mass of the air at state 2, which is leaving. So that'd be air 2. And we can say the mass flow rate of the dry air is constant throughout the system. And so we can just say mass flow rate 1 equals mass flow rate 2, which we can just call mass flow rate of the dry air. So single inlet, single outlet case for the air. Now, in terms of the water, you will also include the vapor as part of this. Well, if we do this, we have the change in mass of the water with respect to time inside the system. So this is steady state, so that goes to 0. And then in terms of the flows, we'll have a mass flow rate of vapor coming in, a mass flow rate of vapor leaving. So we could say m dot vapor 1 minus m dot vapor 2. And leaving, so minus m dot of the liquid water. Now what we're going to note is the liquid water leaving the system. Well, if we wanted to, we could change this. Since we know it's a liquid, we could also call this m sub f because it's liquid. I'm going to just stick with water to use the same nomenclature as before. If we go ahead and rearrange and solve for this value, we get the mass flow rate of the water. This is equal to the mass flow rate of the vapor at 1 minus the mass flow rate of the vapor at 2. Now, what we did in the previous example that we kind of worked through was that we used the equation that we know the mass flow rate of the vapor can be written in terms of the humidity ratio times the mass flow rate of the dry air. And so we can say now is the mass flow rate of the water. Substituting in, mass flow rate of dry air is constant through the system, so we can go ahead and bring that out. Mass flow rate of the dry air now times the humidity ratio at 1 minus the humidity ratio of 2. And so that was the equation that we pointed out on the previous slide. And there we go. When we applied conservation of mass, we were able to get to that equation. Now, in terms of the energy balance, we have to go ahead and write that out. So writing out conservation of energy for the system, we have the change in energy within inside the system with respect to time that goes to 0. This is going to equal the heat transfer rate in minus the rate of work out. Plus then we have the summation of all the mass flow rates in enthalpy in plus the kinetic energy plus the potential energy minus now the sum of the mass flow rates out times the enthalpy plus the kinetic energy plus the potential energy. And so in terms of the analysis, well, we are going to have some heat transfer. So cooling coils mean that we have heat transfer rate leaving the system, so Q dot out. And so we can say, well, 0 equals a minus Q dot out now. We have no turbine or compressor, so we can say that the work goes to 0. We can generally, for our thermodynamic analysis, neglect kinetic and potential energies. So what we're left with now is the summation of all of our mass flow rates. And so if we think about that, we'll have a mass flow rate of air. And so the air was constant, so we can bring those together. The enthalpy of the air at state 1 minus the enthalpy of the air at state 2. Then we'll have to do our water vapor. So we have the mass flow rate of the water vapor entering the system times the enthalpy of the water vapor minus the mass rate of the water vapor leaving the system times the enthalpy of the water vapor leaving the system. And then we have to take into account the mass flow rate of our liquid water of the system. So minus m dot of the water times h. We'll just go ahead and nomenclate, put h sub w. Now, in the previous example that we saw in class yesterday, we were able to combine some terms. So let's go ahead and set ourselves up to do that. So flipping this to the other side, I have the heat transfer rate out. This is equal to the mass flow rate of the dry air. Now we have the enthalpy of the air at state 1, and we can use this trick that we did over here with this substitution, get the mass flow rate of the vapor in terms of the mass flow rate of the dry air. And so when we do that, we'll have plus the humidity ratio at 1 times H sub G1. I'm going to go ahead and put an extra set of parentheses here. Then we'll have minus the enthalpy of the dry air at state 2, H sub air 2, plus the humidity ratio at 2, H sub G2, doing that same substitution. And then we'll use the boxed red equation over here to get the mass flow rate of the liquid water in terms of the dry air. And so this would be W1 minus W2 times the enthalpy of the water. And so we have everything in terms of the dry air setup. Now what we can do is we'll recall this combination right here. This would be basically the enthalpy per unit mass of dry air. This would be the enthalpy of the combined mixture per unit mass of dry air. So we could call that H1 and H2. And so what we get is we have the heat transfer rate out. This is going to equal the mass flow rate of dry air, enthalpy of 1 minus the enthalpy of 2. And then we'll have minus, in this case, we'll have the parenthesis humidity ratio of 1 minus the humidity ratio of 2 times the enthalpy of the water. Then we'll add a parenthesis. And so this will be the form that we will want to use. And we'll see this in the example problem. This is the solution that we want. Now, the one thing that I'm going to go ahead and note at this point is because we have the water leaving, so this is going to be a liquid because it has condensed, we will assume that this can be modeled as a saturated liquid. And so the saturated liquid condition, well, remember that is a quality equal 0. Quality is 0. That means we will have the F side of the table. And so we can say is in this case, I'll do it over here, the enthalpy of the water that leaves, this will be the enthalpy on the liquid side of the table at the given temperature. So at whatever temperature that leaves at. So we'll have another table lookup that we need to do. But once we have that, we'll be able to complete the cooling and dehumidification calculation. Okay, so that is the cooling and dehumidification setup. So let's go ahead and switch gears and let's take a look at an example problem for the cooling and dehumidification setup. So if you're okay with having all of this, I'll go ahead and keep those changes. That way we can go ahead and go back and look at them. But let's go ahead and shift gears into working the example problem that was posted. Okay, so this example problem should look fairly familiar because we are going to be doing a cooling and dehumidification process. And so in this case, we have humid air coming in at 1 atmosphere. It's going to have a temperature of 90 degrees Fahrenheit, and it's going to have a 90% relative humidity. We're going to cool it down to 50 degrees Fahrenheit while the mixture pressure remains constant, so 1 atmosphere. So basically kind of like an HVAC application. We're going to be providing cooling to kind of the air entering a building. We're asked to calculate the amount of water in pound mass per pound mass of dry air, and we're also asked to calculate the water vapor that I should say condenses, so that would be pound mass of water per pound mass of dry air that condenses. And then we're also asked to calculate how much heat we have to pull out of the air during this process, and that will be done on the per unit mass basis. And so that is what we're going to be looking for. We're given one last piece of information here, and that is that the liquid water is going to be leaving the system at 60 degrees Fahrenheit. So let's go ahead and get started. Let's write down all of our known parameters. And so in terms of our known parameters, we have the temperature at state 1. This is the dry bulb temperature. This is going to equal 90 degrees Fahrenheit. In terms of the other parts that we know, we have a relative humidity of state 1. This is also going to equal 90%. And we have a total pressure, so mixture pressure, equal to 1 atmosphere. In terms of the English unit system, that'll be 14.7 psi absolute. So that is our state 1. In terms of state 2, we are given the second temperature. T2 is going to be 50 degrees Fahrenheit. And we're also given that we are going to have condensation. So when we know that there's condensation happening in a cooling process, we know that the exit state is going to have a relative humidity of 100%. Now, if we look at the picture, it also tells us that in kind of a given format. So something to pay attention to. Now, in terms of the pressure, we know that the mixture pressure will remain constant, and so P1 will equal P2 for this setup. So that is what we know. What we're going to be looking for in terms of the find statement. Well, we were told for the first part, we're looking for the mass of the water vapor that condenses. So this will be the mass of the liquid water divided by the mass of the dry air. And since we note this is an open system, we're going to do this in a mass flow rate per mass flow rate calculation. And so even though it says a pound per pound, we'll note that it's a pound per second over a pound per second, and the seconds will just cancel out. So that will be the first thing that we're looking for. The second thing that we were asked to look for is the heat transfer of the system that's leaving. So we'll note that we have heat out, so Q dot out, divided by the mass flow rate of the dry air. And so that will give us the BTU per second divided by pound mass per second. And so that gave us our BTU per pound mass. And so in terms of our system setup, we have now heat transfer out of the system. And we'll note on the the right hand side, we'll have mass flow rate of the dry air entering. We'll have a mass flow rate of vapor entering at state 1. On the left-hand side, leaving, we'll have a mass flow rate of dry air at state 2. And we'll also have a mass flow rate of vapor at state 2. Now we still have one more mass flow rate to account for, and that is going to be the condensate removal. So as we have water accumulate, it's going to drop out of the system, and we'll call this mass flow rate of the water leaving the system. So m dot w in terms of our nomenclature. Now, if we really wanted to, we could also go ahead and note that this state was not labeled, so we'll call that state point 3. We know that the temperature here at state 3, and we forgot to write this down, T3, this is going to equal 60 degrees Fahrenheit. And so we have everything now that we're, in terms of the setup, taken care of. Okay, so let's go ahead and write down what we need to assume to help us get from our known conditions to our find statements. Now, in terms of the setup, we're going to have an open system. The open system analysis is going to be the key thing. We have an open system. We generally want to assume that it's going to be a steady state system. So we'll put those two together. We'll note that we have an ideal gas setup for the air, and we'll assume that it's also an ideal mixture. So we can make those assumptions. We'll note that we want to ignore the kinetic energy and the potential energy of the gas. And so we said we'll just neglect those changes, and we can lastly assume that this entire process was done about 1 atmosphere, which means that we can take the psych chart and we can use that for this process. So we'll be able to reference that. And so once we have all of those assumptions down, we can go ahead and push forward into the analysis. Okay, so in terms of the analysis, we saw in the previous kind of math that we did, we said, okay, there's going to be 3 main things that we need. We have conservation of mass for the air, conservation of mass for the water, and then conservation of energy. And so we'll begin by doing the conservation of mass, and we'll start with air. In terms of air, we had dm of the air dt. That we said was going to go to 0 because it's steady state. And we'll have the sum of all the mass flow rates of the air in. And so we have the mass flow rate of the air at state 1 minus the mass flow rate of the air at state 2. And so we end up with is the mass flow rate of the dry air is going to equal a constant throughout the system. And so we can just call that the mass flow rate of the dry air. We can negate the subscript. So we just have mass flow rate of the dry air now. Okay, so that helps us in the next step, because the next step we want to do is do conservation of mass for the water, and we'll include also the vapor in terms of this analysis. And so for this, we can say the change in mass of the water inside the system with respect to time. So this value goes to 0 because of the steady state assumption. And we said, okay, that has to equal the mass flow rates of the water coming in. In terms of the mass flow rates of the water, we have, if we scroll up a little bit, we have the mass flow rate of the vapor entering, vapor 1. And so that's the only water flow entering. But we have 2 mass flow rates leaving. We have the mass flow rate of the vapor at state 2. And we have the mass flow rate of the liquid water. And so we have 3 terms in this setup. Now, like we did in the previous example, we said we know this is equal to 0. And so what we'll do is solve this for the mass flow rate of the liquid water. We'll note that this becomes the mass flow rate of the vapor at state 1 minus the mass flow rate of the vapor at state 2. So we just have the change in the water vapor. And at this point, we'll go ahead and take advantage of the fact that we know that we have the humidity ratio, so it equal the mass flow rate of vapor over the mass flow rate of the dry air. And so we can say the mass flow rate of the vapor at any state is equal to the humidity ratio times the mass flow rate of dry air. And so if we do that, we'll note that we'll have air at state 1, air at state 2, but we said before those two are equal. So we'll go ahead and do the math to combine these, and what we'll find is the mass flow rate of the water that is condensing out is equal to the mass flow rate of the dry air times now the humidity ratio 1 minus the humidity ratio at state 2. Okay, so that was the answer we got on the previous setup. But we don't have a mass flow rate of the dry air. We were told that we had to find the mass flow rate of the liquid water per mass flow rate of dry air. And so what we'll do is we just said, well, we have mass flow rate of dry air, we have mass flow rate of the liquid water. And so what we'll do is we'll just go ahead and divide both sides through by the mass flow rate of the dry air. And what we'll get is the value will be the difference in the humidity ratio. So W1 minus W2. And so at this point we said we need to calculate the humidity ratio of 1. We need to calculate the humidity ratio of state 2 to be able to proceed. So let's go ahead and do that calculation. So we are going to come over here. We'll go ahead and take a look at state number 1. This is the entrance condition. And so we know at the entrance condition, we have pressure 1. This is 1 atmosphere. This is going to be 14.7 psi absolute. We said, okay, that was the first thing that we were given. The next thing that we were given was the temperature 1. This is equal to 90 degrees Fahrenheit. And so we'll have to do something with that. We were also given the relative humidity now at state 1, which is also equal to 90%. So those were the given values. But what we want to calculate is we want to calculate the humidity ratio at 1, which we said would be the mass flow rate of the vapor at state 1 divided by the mass flow rate of the dry air. Now, if we go back into our definitions, we'll note that this ratio was also equal to 0.622 when we have air and water. And then we have the partial pressure of the vapor at state 1 divided by the total mixture pressure at state 1 minus the partial pressure of the vapor at state 1. So at this point, what we've realized is we are missing the partial pressure of the vapor at state 1. So we need to find that value. Now, to do that, what we want to do is we want to go ahead and move up one variable here. So we know that we have the relative humidity that was equal to 90%. And by definition, this was equal to, to the mass that we have of the water vapor divided by the saturation condition. Now, when we did the mathematics on that, what we found is we have the partial pressure of the vapor at 1, now divided by the saturation condition at state 1. And you said, well, if we take this, we can now substitute for P vapor 1. This is equal to the relative humidity times P sub G1. And so we can substitute that in here. So we'll do 0.622. And then we'll have the relative humidity 1 times the saturation condition of 1 over the total pressure minus the relative humidity at 1 times the saturation condition at 1. And so at this point, we only need the saturation condition to proceed. We said, well, is there anything that we can use to get the saturation pressure? We said, well, this saturation pressure, because it's on the vapor dome, all we need is the temperature. It's only a function of the known temperature at this state. So well, we have the temperature T1 right there. So if we go ahead and take this to the thermodynamic lookup tables, we can get the P sub G1, our saturation pressure at state 1. This is going to equal 0.6994 psi absolute. And so once we have that value, we could go ahead and put that in there, and we can say, well, that value already went to there. We have everything at this point to calculate our humidity ratio at state 1. And so the humidity ratio is going to be a plug and chug value. And so what we'll get is 0.027811 The units on this are going to be a pound mass of vapor divided by a pound mass of dry air. And so we have the humidity ratio at the initial condition. Okay, so one of the two values has been checked off, so we can go ahead and check that off. So what we need is state 2. Now, I'm going to go ahead and note that we have some other things that we're going to need to look up here. And so we'll come back and look those values up here when we need to do some state 1 lookups. So I'm just putting those in, so I left myself a little bit of room. But we can go ahead now and proceed on to state 2. So state 2, we need to find the humidity ratio. We'll note that the pressure of state 2, this is the same as the pressure of state 1, 14.7 psi. But we already wrote that up there. And so the next thing that we know is we know the temperature of state 2. Temperature of state 2 was 50 degrees Fahrenheit. And we lastly know that state 2 is going to have a 100% relative humidity because there was condensation in this process. And so using these variables, we'll go ahead and calculate the humidity ratio at state 2. Noting the form that we used in the first one, we'll have 0.622. And we said, well, I'll just go ahead and write this out. P vapor 2 over the pressure of 2 minus P vapor 2. We said, well, P vapor 2, this is just going to be our humidity ratio at 2 times P sub G2. And so we'll know P sub G2 is going to be different because we have a different temperature. And so we can go ahead and solve for the humidity ratio 0.622 times now our relative humidity of state 2 times P sub G2 over P2 minus the relative humidity times P sub G2. And we'll note that because of the setup, because we're at the saturation condition, this case simplifies to PV2, that will equal P sub G2. And that's just because we have phi equaling 1 for all intents and purposes. All right, so like the last time, all we need to do is get the saturation condition. We have our temperature. We said once we know the temperature, we can just go ahead and complete the lookup. So P sub G2, this is going to equal 0.017812 psi absolute. Oops, sorry, there shouldn't be a first zero there. Got one too many zeros in there. So it'd be 0.1782 psi. And so once we get that value, we said this becomes a plug and chug problem. So we get now the humidity ratio at state 2. This is going to equal 0.007629. The units are going to be a pound mass of vapor divided by a pound mass of dry air. And so there we go. We have humidity ratio 1. We have humidity ratio 2. And so we can check this off the list. We have both of these values. We can go ahead and calculate the answer to part 1. Again, this is just a plug and chug style problem. And so what we'll get when we go ahead and put this into our calculator is the mass flow rate of water that condenses per mass flow rate of dry air. It's going to equal 0.02018 pounds of, or I should say pound mass of vapor per pound mass of dry air. Or roughly, if you want to think about, there's about 2% of the total mass here, or mass of the dry air would come out. Kind of a weird way to think about it, but most of the mass that we had flowing through our system is going to continue because most of that mass was in the air. And so we'll note at this point that was the answer here to part 1. and we can continue on. And yes, so we'll take a look at that, and we'll be able to show that we can look up W1 and W2 on the psychometric chart. And if we have a high enough resolution chart, we'll show that it's pretty good in terms of the estimates. And so that's what I wanted to do in this example, is do the mathematics and then show how well that lines up with the psychometric chart. So we're gonna do that here in kind of the end part. We'll do a comparison. Okay, so once we've done all of that, we can say that was part one. So part two, we are asked to find the heat transfer rate out per mass florid of dry air. So we'll note that. So we're looking for Q dot out per mass florid of dry air. Talking about heat transfer rates, that means conservation of energy. So COE. In terms of the setup, just to get this down, we have the change in energy inside the system with respect to time. This is going to go to 0, steady state. This is equal to the heat transfer rate in minus the rate of work that we have leaving the system, plus then we have the summation of the mass flow rates in, the enthalpy in, plus the kinetic energy in, plus the potential energy in, minus the sum of the mass flow rates out, times now the enthalpy out, plus the kinetic energy, plus the potential energy, and there we go, we've completed the setup. Now what we noted before is that there was going to be no work. We assumed that there was going to be no change in kinetic or potential energies, so we can cross those out of the equation. And so what we're left with is heat transfer rate in, which we note we can say, well, this is just a minus Q dot out. So we just flip the signs, since we know the direction in this case. And then now we have to do all of our mass flow rates times their corresponding enthalpy. So if we go through the list, we'll start with the mass flow rate of the dry air. We'll note the air in and air out are the same, so we end up with the H air of 1 minus H air of 2. And then we have the water vapor. So we'll have the mass flow rate of the vapor at state 1 times the enthalpy of the vapor coming in at state 1, minus now the mass flow rate of the vapor at state 2 times the enthalpy of the vapor at state 2, minus now the mass flow rate of the liquid water times the enthalpy of the water that's leaving. Okay. And so a few things that I want to go ahead and note at this point. So in this case, we have the difference in the air enthalpies. So that could be C sub P of air, T1 minus T2. So that's the first thing I want to note. Then we're also going to note that the mass flow rate of the vapor, this can be related to the humidity ratio times the mass flow rate of dry air. This can be the humidity ratio times the mass flow rate of dry air. And this value we solve for up here. This would be the humidity difference in the humidity ratio W1 minus W2 times the mass flow rate of dry air. So if we wanted to make all of these substitutions, we can. What I'm going to do is I'm going to go ahead and keep the enthalpies of the air in terms of H air 1, H air 2, just to kind of keep things consistent. And I'm going to try and bring things together here. So solving now for the heat transfer rate out, so Q dot out. This is going to give us, well, we'll have the mass flow rate of dry air now. Put a parenthesis. And then I'm going to go ahead and put another parenthesis here. We'll have H of the air at state 1. And then we'll have plus now the mass flow rate comes out, plus now W1 times H sub G1. I'll put a parenthesis there. Now we'll have minus, and we'll do another parenthesis, H of the air at state 2, plus, and we'll have a now minus, or plus a W2 here. Mass flow rate of dry air came out, so then we'll have H sub G2. And then we have the last term over here. Mass flow rate of air comes out, so we have minus W1 minus W2 2 times the enthalpy of the water, and then we'll have our final parenthesis. Okay, so we see that we have this form, but we wanted to solve again for heat transfer per unit mass of dry air. We know we have mass flow rate of the dry air, so we can do now is just go ahead and solve for the heat transfer rate out per unit mass of dry air. So now let's go ahead and substitute this in. What we would have is C sub P of the air times T1 plus humidity ratio 1 times H sub G1. Put that in parentheses. Minus, do C sub P of air T2 plus the humidity ratio of 2, H sub G2. Put that in parentheses. And we'll have minus W1 minus W2 in parentheses times the enthalpy of the water. Now what we're going to do is we're going to say, well, this combination parameter right here, this was all done per unit mass of dry air. So that's the mixture properties per unit mass of dry air. So the mixture enthalpy per unit mass of dry air at states 1 and 2. And so again, what we're going to note here is the enthalpy as we've defined it. This would be C sub P air times the temperature plus now the humidity ratio times the enthalpy of the water vapor at that state. Special thing that we're going to note is this temperature is going to be given in degrees Fahrenheit, because what we'll do is we'll look this value up, and we had a delta T up here, so we can use Fahrenheit rather than absolute temperatures in that part of the equation. Okay, so finally bringing it all together, what we're going to do is we'll have the heat transfer rate out per mass flow rate of dry air. It's going to equal the enthalpy of 1 minus the enthalpy of 2 minus the humidity ratio of 1 minus the humidity ratio of 2 times the enthalpy of the water. And so at this point, we need to do some calculations in terms of the lookups. We're going to need the specific heat of air. We're going to need the enthalpy of our two different states for the vapor, and then we'll also need the enthalpy for the water. So let's go ahead and do those lookups. So I'm going to go ahead and scroll up here back to state 1. And so we left ourselves some room for H sub G1. And if we go to the table lookups, this is going to be 1,100.4 BTU per pound mass in that setup. So that's a 0.4. And so we should also go ahead and look up the specific heat for air. And so if we do that, we'll get that that's 0.24. And the units on this are going to be a BTU per pound mass. And technically this would be Rankine, but since this is a delta Rankine, that would be the same thing as a delta Fahrenheit. So we'll just put an F in that portion. Okay, so there we go. We have state 1 in terms of the enthalpy. So now let's go ahead and finish state 2. So state 2, we're going to need H sub G2. Again, this is only a function of temperature. And so what we'll do when we do the lookup is get this to be 1,083.1 BTU per pound mass. So we have the enthalpy of state 2. Okay, so one thing we're missing is now the enthalpy of the water leaving. And so if we go ahead and take a look at state number 3, state number 3, the temperature T3 was equal to 60 degrees Fahrenheit. This is the temperature of our water. And we said, well, we can assume that this is a saturated liquid. Our saturated liquid quality is equal to 0, which means that we can look up H sub F at this temperature. So enthalpy of the water, note this is the enthalpy in terms of the F side of the table. And if we go ahead and look that up at the given temperature, this is going to equal 28.08 BTU per pound mass. Okay, so that should give us everything that we need at this point. And so what I'm going to go ahead and do is I'm going to go ahead and calculate the individual enthalpies here. So we'll get enthalpy of state 1. We'll show that this is 52.2. Units are going to be a BTU per pound mass of dry air. And we can go ahead and calculate the enthalpy now, state 2. State 2, this is going to be 20.26. This is going to be BTU per pound mass of dry air. Okay, and so once we've made those individual calculations, we can come over here, finalize our work. So we have Q out over the mass flow rate of the dry air. And when we do this, we'll find that the value is going to be 31.37 units are going to be a BTU per pound mass of the dry air. And so there we go. We've completed the second calculation. All right, so I know that was a lot to get through, but we could have also done this a separate way. So I'll give you a little bit of time to finish writing, and then what I'm going to do is I'm going to move on to the psychometric chart on the next page here. All right, so I'm going to go ahead and scroll down. And so on the next page, we have the high resolution psychometric chart. So what we want to do is we want to use this to see how well we can estimate what happened. And so in terms of drawing this, I'm going to try and use red. And so this is going to be, again, trying to find our different state points. Now what we'll do is we'll start with state point 2, because that's going to be a little bit easier to find. State point 2, we had our dry bulb temperature equaling 50 degrees Fahrenheit. So on the chart, we have the 50 degrees here. So go ahead and just move vertically along this line till we get up here to the 50 point. All right, so at the 50 point, we can now go ahead and calculate parameters. So the first one we'll do is we'll do enthalpy. So if we followed this line, we'd go right up like this. We'll note that that'd be 20 plus whatever that delta is. And if we spent the time to actually count out what each of these little delta lines are, those are going to be 0.02. So we'll find is the enthalpy at state 1 is going to equal 20.2 BTU per pound mass of dry air. So that is the first one. Second thing that we should do is we can go ahead and draw our line across here, trying to do this as constant as possible. I think I started to deviate there, but should be pretty close here. And so if we came all the way over here, that would be basically, it should be 2 individual steps between there, and so each of those steps is 0.0002, and so that means the humidity ratio at state 2 we'd estimate that as 0.0076, because we're 2 below that, so 0.0004 below 0.008, and so that's that value we're reading right there. And so the units on this would be a pound mass of vapor per pound mass of dry air. And so if we compare those two values to what we got up on the top, well, enthalpy state 2, 20.2 versus 20.26, that's probably pretty good. Enthalpy, or our humidity ratio state 2, 0.0076, and this one was 7629. So pretty good in terms of the estimates. And so let's go ahead and try this at state 1. State 1, we had a temperature T1. This is equal to 90 degrees Fahrenheit. And so we'll go ahead and try and draw this all the way up. So again, this just takes a little bit of time. But if we follow this line of constant temperature all the way up until we reach the other thing that we knew. The other thing is that we knew we had a 90% relative humidity, so we're going to follow that line up to this point. And so we find where those two converge, which is going to be right here. This is going to be state number 1. This is state number 2. And so if we go ahead and try and do a lookup on the values over here, trying to keep this constant, we'll see that that's right about 0.028 pound mass of vapor per pound mass of dry air. And so if we just do a quick comparison on humidity ratio, so this is 0.0278, that basically rounds to 0.028. So yeah, pretty good combination there. And then if we go ahead and do a line up here along the line of constant enthalpy, what we'll find is this value becomes 52.2. And so that's basically what we got, BTU per pound mass of dry air. So note that is H2. Okay, so now we'll finish this off by doing essentially what the process was. So we have state 1, we have state 2. And so in terms of the process, the first thing that we did is we provided just straight simple cooling until we reach the saturation condition. And then once we reach the saturation condition, we're just going to move along the saturation line at 100% relative humidity until we got to state 2. And so again, first we went left, then we went down and left along the psychometric chart. And so that is exactly what the psychometric chart would do. And so if, again, instead of doing all of the calculations by hand, if we wanted to just use the chart now to look things up, we could do that. And if we have, like I said, if you have the high resolution charts, which I've provided the PDFs for, so if you want to use those over the psychometric charts that are in the textbooks, you can do that. And we can make these substitutions with reasonable accuracy at this point. And so that's what I wanted to show with this psychometric chart. So again, like I said, if you want to use the high resolution ones, the PDF has been provided for you to use this in place of the ones that were included with your homework assignment, which was the value or the psychometric chart from the textbook. Okay, so that is going to conclude today's lecture and example problem. So if you do have any questions about any of this, please let me know. Otherwise, just to give you a heads up, next week we will be finishing up the PowerPoint where we'll do the adiabatic mixing of flows. We'll do an example problem where we deal with adiabatic mixing, and that will complete the psychometric portion of this class. And we'll be moving into the new topic towards the end of next week, which is combustion. So otherwise, have a good rest of the day and enjoy your weekend, and I will see you in class on Monday.